Section 3.3. Going to take a look at asymptotes. There are three types of asymptotes. And we'll go through this hopefully pretty quickly. First is, how on earth to even spell asymptotes? Well, there it is. Okay, three types that can occur. You can get vertical, you can get horizontal, and you can get slant. First, let's take a look at vertical. So, three different types. First type, vertical. Vertical occur where you get a 0 in the denominator. The idea here is you're going to have some x value that is not in the domain. So for example, if you have something like y equals 2 over x minus 4, where's the problem point or value? It's at x equals 4, isn't it? Okay? So to graph this, actually, let's cheat and do this a different route. We can do this like this. There. How's that look? That'll look a little better, hopefully. At x equals 4. So we come over to 4. 1, 2, 3, 4. You got a vertical asymptote. Like that. Vertical asymptotes are kind of electrified barbed wire fence. Do you ever want to cross that or mess with it? Yeah, probably not. It's going to hurt. Okay? When you are graphing functions, they do not cross vertical asymptotes. They don't. What will happen is the function will run close to it. So you get a function that'll do something, for example, like this, and get closer and closer, but it will not touch it, it will not cross it. Okay? They don't. Another scenario that can happen is if you have something like y equals, let's say something like x plus 1 over x plus 5 times x minus 3. Okay, what's going to wind up happening here is a couple things. First, it's pretty easy to spot a root. A root is where the y value is 0. Now remember, when you have a rational function, a fraction, the function or the fraction can equal 0 if the numerator is 0. Okay? So this means that x equals a -1. We've got a 0 right there. It also means, or we can also see from this function, that at x equals -5, we get a 0, but this time it's in the denominator. So if we go 2, 3, 4, and -5, we're going to have a vertical asymptote there. Notice at x equals 3, 1, 2, 3, we're going to have a vertical asymptote there. And then it's a matter of fitting the function in to that set of parameters. Now, this also has a horizontal asymptote. Horizontal asymptotes are different from vertical asymptotes. Horizontal asymptotes, the function can cross. The graph can cross a horizontal asymptote. And you will see situations where if you have a horizontal asymptote like this, you will see scenarios where a function may come up, cross the horizontal, and then come back into it and run asymptotic. Okay. For this particular function here, you have vertical asymptotes at x equals -5 and x equals 3. You also have a horizontal asymptote at y equals 0. Now, how on earth do we get the horizontal asymptote? Well, we'll talk about that in a couple minutes here. I'll make sure the verticals are working. Does this make sense on vertical asymptotes? Vertical asymptotes are where the denominator is 0. Now, one thing that sometimes causes people some confusion is, well, gosh, what if I have something like this? Oh, let's say x minus 3 over x squared minus x minus 6. What am I going to do with that? Well, first thing to do is to go ahead and factor the denominator, and that denominator factors into x minus 3 times x plus 2, doesn't it? Okay. These x minus 3's cancel. That removes one of your vertical asymptotes, doesn't it? Okay. And what you wind up with is the function 1 over x plus 2, leaving you with a vertical asymptote only at x equals -2. Does that make sense to everybody? Okay. So, for the vertical asymptotes, does that sound familiar to you? Look familiar? No big surprises there? Okay. Should be stuff that you'd seen somewhere or another in an algebra class. Now, the second type of asymptote that you can get that we've talked about a bit is horizontal asymptotes. With the horizontal asymptote, they're going to occur in one of two scenarios. The first scenario is where the degree of the numerator equals the degree of the denominator. What do you mean by that? Well, an example, this would be something like y equals 4x squared minus 7x plus 8. I'm intentionally saving some space there. Okay, that isn't by accident that there's so much space between the quadratic and the line for the fraction. Over, let's say 7x squared plus 4x minus 9. When you have a scenario where the degree in the numerator equals the degree in the denominator, see if the highest power in both of them is x squared, isn't it? Okay. When you get that scenario, your horizontal asymptote is going to be at y equals 4 over 7. To get that, all you do is you take whatever the leading coefficient in the numerator is over the leading coefficient in the denominator. And ta-da, you've got it. Well, that's all well and good, but how does that really work? Why is it that that works out like that? Well, the way to look at this, or one way to look at this, is the highest degree in the numerator is x squared. Everybody buy that? Highest degree in the denominator is x squared. If we take this fraction and we multiply it by 1 over x squared over 1 over x squared, we're not going to change the function. This function is actually equal to 1, isn't it? Because anything over itself is just 1. However, distribute this 1 over x squared, what we're going to wind up with is 4x squared over x squared minus 7x over x squared plus 8 over x squared, and that's in the numerator. In the denominator, you're going to have a 7x squared over x squared plus a 4x over x squared minus 9 over x squared. Okay, well that's all well and good, Chuck, but what on earth is that going to do other than give us 6 fractions where we once had 1? Okay. What you then want to think about is for a horizontal asymptote, you want to think about what the function is doing as you move toward infinity or as you move toward negative infinity. Horizontal asymptotes really describe what's going on as you get way out on the ends of the function. Does that make sense? So what that's really saying is we want to think about this function over here as x approaches either infinity or negative infinity. Make sense? If we think about it in that setting, what will wind up happening is the x squared over x squared will cancel, and that'll just leave us with 4 in that first term, won't it? In the second term, an x will cancel, and that'll leave us with 7 over x. Now think about the value of that fraction as x gets really big. As x gets really big, that fraction approaches a value of what? 0, doesn't it? So this term approaches 0. The 8 over x squared is going to be in a similar situation. And that fraction is going to approach 0 as well. In the numerator, all we're left with is 4. You see it? Everything else is gone. And that same scenario is going to play out in the denominator, isn't it? In the first term, the x squareds will cancel, leaving us with just 7. In the second term, well, one of the x's will cancel, leaving us with 4 over x, but as x gets really big, 4 over x is going to go to, as you already know, 0. And the minus 9 over x squared, well, gosh, that's headed the same direction, 0. And this thing simplifies to just be 4 over 7. So if we were graphing this function, it would have an asymptote, a horizontal asymptote, at 4/7. Now the graph is going to do whatever it wants to do in the middle area. But as you get way out on the tail end, it's going to settle in at 4/7. Does that make sense? Everybody good with that? Hey, as you go to negative infinity, where does this function go to? And this is where you have to be careful, because the question is, do you have positive or negative leading coefficients? Do you have an even or an odd degree? If it was x cubed, well, let me throw it at you this way. If it was x cubed, would that make any difference, or would it all cancel out? It would all cancel out, wouldn't it? Because you have an x cubed in the numerator and an x cubed in the denominator. And even if the numerator is negative, the denominator will wind up negative as well. Does that make sense? And a negative over a negative is positive. So as you go to negative infinity, in this case, where's the function going to level out at? 4/7. making up the middle part. I don't know what the middle part's doing. Okay, so understand that if you graph this thing, you're thinking, geez, that's not what I got. It's probably true. What I'm really interested in here is the tail behavior. Okay, so the first thing to focus on whenever you walk up to a rational function and you're thinking about domain and you're thinking about asymptotes, first thing to focus on is where will the denominator return a value of 0. Those are numbers that you can't have in your domain. You can't use those. They break the function. That will give you vertical asymptotes. The function never crosses a vertical asymptote. Never. It doesn't do that. The second thing to look at is, first, is the degree of the numerator equal to the degree of the denominator? If the answer is yes, then you're going to have an asymptote at whatever fraction is formed by these two leading coefficients. Does that make sense where that comes from? It's pretty easy to read, isn't it? You just walk up. If there's a tie for the highest degree, if it's an x to the 5th in the numerator and the denominator, you just look at the numbers and boom, without doing anything other than looking at it, you can write down what the horizontal asymptote is going to be. And it's just that cool, just that easy. Second place you can get a horizontal asymptote is if the degree of the numerator is smaller than the degree of the denominator. Okay, so what's that going to look like? Well, keeping it fairly simple, let's say we have x plus 4 over 3x squared minus 9x plus 5. I'm not dealing with vertical asymptotes here. Okay? To get the vertical asymptotes, you would take that 3x squared minus 9x plus 5, set it equal to 0, wouldn't you? And whatever x values give you 0 are your vertical asymptotes. Translation, I hope you've got that quadratic equation on your calculator. Because if you do, you can fire it up, put in the 3x squared minus 9x plus 5, and boom, it'll give you your vertical asymptotes because they're the x values. Just that easily, you can get the vertical asymptotes off of this. Does that make sense? Okay, so we can get those done fairly easily in some cases. As far as the horizontal asymptote, if we multiply the numerator and the denominator by the reciprocal of whatever the highest power of x is, in other words, we're going to divide everything by x squared. Okay, does that make sense to everybody where we're headed now? What this is going to give us is x over x squared plus 4 over x squared, that whole thing over 3x squared over x squared minus 9x over x squared plus 5 over x squared. Now, we've got that done, and now what do we apply to this function? Well, if we're interested in horizontal asymptotes, we're concerned about where is this thing behaving way out on the ends, aren't we? To get way out on the ends, you apply the limit as x goes to infinity or negative infinity. Does that make sense? So we're going to do this same deal. This limit as x goes to infinity. Now, in this case, as x goes to infinity, this is going to 0, this is going to 0, so the numerator is going to be 0. In the denominator, this fraction will approach 0, as well as this fraction. However, the first fraction will approach a value of what? 3. 0 divided by 3 is what? 0. If the degree of the numerator is smaller than the degree of the denominator, you will have a horizontal asymptote at y equals 0. What does y equals 0 look like on the graph? Where are we? It's the x-axis, isn't it? Okay. This is going to be the x-axis. This function can have roots. This function can have points at which it crosses the x-axis. Okay? So this function can do stuff, and I'm just making it up here. You can cross the x-axis a couple of times and come back in like that. Where it crosses the x-axis is what? Would that be where the denominator equals 0? Or where the numerator equals 0? And the thing to remember is, where it crosses the x-axis is where the function has a value of 0, which means the numerator has to be 0. Oh, wait a minute. Well, that's kind of weird. It even erases the... Okay. Never erased the coordinate axis. That's interesting. If you have a coordinate axis, where it's going to cross that coordinate axis is where the numerator is 0, which in this case is going to be -4. It's going to cross there. Where the denominator is 0 is where you're going to have what? Aren't those going to be vertical asymptotes? How could we get those? Let's say you've got something like that. Does anybody have the quadratic equation on their calculator? If you don't, you need to go over to the math lab and get it. Okay? We're going to be using it all year. You're going to hear me comment again in January, February, March, and April. You need to get it. And it's going to make your life a lot less painful if you get it. But let's say right now you're thinking, crud, I forgot it again. And on Friday's quiz, it's, oh, rats, yeah, I need to get around to that, but I need it right now. And I don't have it. What can you do if you don't have it right now? Well, what you can do is hope and pray that your calculator comes on. Okay. If you have problems with your calculator, pop it off and just kind of roll the batteries, and that'll help sometimes. Sometimes. This one gets used hard, so the batteries may be dead. They may be dead. Okay, so what you can do is you can go into your calculator, set y1 equal to 3x squared minus 9x plus 5, and graph it. I have no clue what that's going to graph to look like, but wherever it crosses the x-axis, okay, are your values of x where you're going to have asymptotes. Okay, so what am I going to do, Chuck, if I don't have the calculator, but I somehow have access to a computer? Okay, well, another route to go is to go to Wolfram Alpha. And solve equals 0. Now, you ready for a new abbreviation in math? With respect to, WRT. With respect to x. That means solve for x. Okay? Press enter. First thing you always want to do is to make sure that what we've actually solved for is what we want. Right below where you've entered things, it'll have an interpretation. Right there. Make sure that what it thinks is what you think has been entered. Well, this does have two roots, doesn't it? Oh, look at there. And they're real roots. That means this thing has two vertical asymptotes. I'm going to switch this over to approximation form. Around 0.74 and 2.26. Does that make sense? Somehow or another, you got to get those two numbers. Now, remind me again, what do those two numbers give us on our graph? Oops. We've got these two numbers, 0.74 and 2.26. What do those numbers mean? Those are places where the denominator is 0, and if the denominator is 0, you have a vertical asymptote. Aha! So we're going to come over, here's 1, 2, 3, 4. 0.74 is going to be something like that. 2.26 is going to be something like that. Make sense? Now, I'm not quite sure what this graph is going to do, but it might do something like this, and it might do something like this, and then in the middle it probably does something like this. I'm guessing, purely guessing. Okay? You can graph it on your calculator. I obviously can't graph it on mine. Time for new batteries. Does that make sense? Okay, so two scenarios where you can wind up with a horizontal asymptote. The denominator and the numerator have the same degree. Secondly, the denominator has a larger degree than the numerator. One last way that you can get an asymptote, and these are kind of strange, or I always thought they were kind of strange, it's what's called a slant asymptote. And with a slant asymptote, what you wind up with a scenario where the numerator is exactly 1 degree bigger than the denominator. So it would be, the numerator would be something like y squared plus 5x plus 6, and the denominator might be something like y minus 1. The numerator is degree 2, the denominator is degree 1. The degree of the numerator is 1 larger than the degree of the denominator. The difference is 1, always 1. If the numerator was y to the 5th and the denominator was y to the 4th, you'd still have slant asymptote. Make sense? Okay. Now the way a slant asymptote would then work, or the way you would compute where a slant asymptote is you would do the division. Well, I don't know why I put y's in here for part of this. I'm sorry. We're not going into multiple variable calculus until January. Those should all be x's. I don't know why those y's got in there. Okay. What you do first, and this may bring back some pleasant memories. Oh no, not this, Chuck. that look familiar from anywhere? Oh, yeah, I remember these. First step in doing long division is you want to take and look at this term. Whatever that term is, you want to multiply this times something or other to exactly match what's in the green. If that would have been a minus 5x squared, we would have a minus 5x up on the top. You want it to exactly match. Then what I'm going to do is to take this and distribute it. And when we distribute it, we're going to get x squared minus x. Okay. Now think back to the good old days. 3 goes into 41. Well, let's see, it goes in one time. That gives me a 3. And then do you add those two numbers, or what do you do to those two numbers? You subtract. The same thing happens here. Whatever you have here, you now subtract. And be sure you distribute that negative. So that's going to give us x squared minus x squared, 0. The x squareds are gone. We have 5x minus a minus x gives us 6x. And we can bring down this plus 6. Does that make sense? Everybody in good shape? Okay. Second move. We want to multiply to make this x in the divisor exactly match our lead term. What do we need to multiply by? Plus 6, yeah. So I'm going to do this time is multiply by a positive 6. That'll give us 6x minus 6. As with the first step, you then subtract. The 6x's will cancel, and we're going to be left with the remainder of 12. Our slant asymptote is going to be y equals x plus 6. It's going to be this. And because we only do this when the degree of the numerator is 1 bigger than the degree of the denominator, okay, our dividend, the thing that we have left, is always going to be x plus or minus. It's always going to be linear, always. Always. And to get then the slant asymptote, you just graph whatever that is. Well, let's see, it's going to be 1, 2, 3, 4, 5, 6. So it's going to be an asymptote that runs like that. Y equals x plus 6. Now, notice something else with this function that we're working with. Does it have any vertical asymptotes? Well, wait a minute. Vertical means that the denominator is 0. Oh, yeah, the denominator is 0 when x is 1. So we're going to have a vertical asymptote like this. And I don't know what it really looks like. Okay? I don't know what it really looks like, but it might be that this graph does something like this. Does that make sense to everybody? To figure out where it actually is, you just plug some points in. So for example, we can plug in 0. We're going to get negative 6. Do you see that if we plug in 0, we get back negative 6? So it's actually going to be way down there. So apparently this first part does stay down, but it does something more like this. see, roots means it's where the function is 0. In this case, the function is 0 when the numerator is 0. And the numerator is 0. Well, gosh, look at that. That thing factors into x plus 3 times x plus 2, doesn't it? You see that? So you have roots at -2 and at -3. Aha! So we go 1, 2, 3. We're going to have a root there. We're going to have a root there. So this thing's going to come up, go like this, come above, come back down, and run asymptotic. Should actually be a nice smooth curve. And if the one section's there, the other section is going to be up where the other piece is drawn. And if you want to check to make sure, does that other piece really wind up way up there? We could plug in something like x equals 2 or 3 into our function and get a y value out. If we plug in, for example, 2, the denominator is going to be 1, and in the numerator we're going to get 4 plus 10 plus 6. Whoa, it's going to be up at 20, isn't it? So at 2, we're way up here, somewhere way up here at the top of the screen at 20, and yeah, I guess it really does go way up there. Does that make sense how these different asymptotes work? I know it's kind of a quick whirlwind tour of asymptotes. Okay. When you graph them on your calculator at times will do some really weird stuff. Like it would do a graph that went like this. And it's going to have kind of a hiccup in it. This chunk right here. And what you need to realize is that jump is not actually part of the graph, but it's your calculator trying to deal with the fact that it can only plot where the pixels are. It's not a continuous thing. Does that make sense? It can only light up certain little spots on the graph or on the screen. And you're going to get jerky things like that. Realize that those are not part of the graph. They're part of the shortcoming of the calculator. That's what happens when you deal with machines. Okay, that's got 3-3 done. Let's take a look at 3-4. Maxes and mins. Let's try this again. Section 3.4. We're going to get into absolute max and mins. Up to this point, when we have solved for maxes and mins, it's always been the case that we've just talked about it being a relative max or min. We don't always know if it's the absolute max or min. Now, that said, there are situations where if you have a graph like this, do you have an absolute minimum to it? Yeah. There's one spot right there where it's an absolute minimum. Or if the graph is a parabola opening downward, clearly you have an absolute maximum. There are, however, scenarios where the graph might do something like this. Does this graph, as it's pictured right there, have an absolute maximum point? And the answer is no. Because is there any place at which it stops, or does it keep going all the way up to infinity? It has a relative maximum right there. On the flip side of the coin, does it have an absolute minimum? Same answer, no. But it has a relative minimum right there. Mathematically, this is fine. You can go to infinity mathematically. However, if you're working for Ford, or you're working for P&G, or you're working for GE, or wherever it is you land, can they make an infinite number of whatever it is? Can P&G make an infinite number of Tide Pods? Nope. I think people stopped eating them, right? That was strange. I assume you're all aware of that, right? A couple of years ago, when why you'd want to eat soap, I have no clue, but oh well. But the catch is, in the real world, nothing goes to infinity. What happens in the real world, as we know it, well, that didn't work so good. Not quite sure what happened there. We'll try this again. Maybe I got the wrong one. Okay, what happens in the real world, if we're talking about Tide Pods, P&G has a maximum number they can make, don't they? They've only got so much production. And we have a minimum number we can make. What's the minimum number of which you can make? 0. So our quantity is there. Let's say this is our profit. If we make none, the profit is down here. Whoa, dude, why is the profit down in the negatives? Because even if P&G shuts the plant down for the day, does it cost them money to have that plant there? Yep. They still have to pay the workers, usually, depending on the country you're in. There are still expenses, so the profit is negative. But what will happen is the profit will do whatever it's going to do, like that. We have a relative maximum here. Why am I not even concerned about relative minimums on this graph? Because we're talking profit. Do you really want to minimize your profit? No, thank you. Okay? We want to maximize profit. So we're going to extend this graph on out. Now, P&G has a maximum level of production. And let's say that the maximum production level is right here. When you are computing your profit and you need to know what level of productivity do we need to establish to maximize our profit, one option would be this value right here. We'll call this Q sub 1. It's one of the quantities that we could use. The other place where a maximum can occur is at the end point. The end point being our maximum production. We'll call this Q sub 2. It's a limit. Another place where our maximum profit could be is right here. It's the other endpoint, and we'll cleverly call this Q sub 0. When you are looking for an absolute maximum, there are several places you need to check. You need to check at all of the points where the derivative is 0. You've got to check all of those, because your maximum profit might be at one of these. Then you also need to check the endpoints, because your maximum profit might actually be over here. This endpoint will not turn up with the derivative, because remember, this is a limit that we've imposed other than by the derivative being 0. This is imposed because of machinery or resources or other things, isn't it? That is not a location where the derivative is going to be 0. Does that make sense? One of the things that will happen in the problems that you'll be given is you will be told the maximum production is 700,000 Tide Pods a day. When they say 700,000, that's assumed to be the maximum, and without even saying it, what is the implicit, understood minimum production? What's the minimum number of those Tide Pods you can make a day? 0. What will happen is you'll be told the maximum. You won't be told the minimum because it's assumed that you already know what the minimum number you can make is. None. Okay? So realize that when these problem statements are made, or even more importantly than a problem in the book, in the real world, when your boss walks up to you and says, hey, look, we can't manufacture more than 50,000 of these things an hour. You, with your background in mathematics, also realize that he's given me, she's given me, whoever has given me my limits. My limits are 0 and 50,000. The 0 escapes most people. Don't let it escape you. Okay? So what's this stuff going to look like? Well, what it's going to look like is something like the following here at first. You're going to be given a function like f of x equals x cubed minus 3x plus 2, and it's going to be on the interval, let's say negative 2 to 3 halves. Where did the 2 and the 3, negative 2 and the 3 halves come from? It's just something made up for this problem. This is just made up, practice, contrived stuff. When you get into production and sales, these numbers are going to be established by what demand is, by what production capacity is, things of that nature. What your contracts read. To solve this for a max or a min point, first thing you do is you take the derivative, which is this 3x squared minus 3. You set it equal to 0. This is going to give you 3x squared equals 3. X equals plus or minus 1. Does that make sense to everybody? I kind of sped through that. Now, your possible solutions are going to be at x equals negative 1, and whatever that works out to be, at x equals 1, and whatever that works out to be, and your endpoints, negative 2, and whatever that works out to be, as well as 3 halves, and whatever that works out to be. How do you get those y values? Plug it into what? The original function. Be careful to always go back to the original function to get your y values. I know that you can do all kinds of cool stuff with increasing, decreasing. We can do second derivatives and do all kinds of analysis on these 2 points, can't we? But in this case, we have not only those, but we have the endpoints. The easiest way to determine what the winning number is to evaluate the y value for each of the points. At negative 2, it's 0. At negative 1, it's 4. At 1, it winds up being 0. And at 3 halves, it's 7/8. Where's your absolute max? Where's the absolute max in this case? It's right there, isn't it? It's the highest y value. Where's your absolute min? Oh, wait a minute. We've got a tie, don't we? Is it possible to have a couple places with the same minimum value? Sure. You got one right there. Does this make sense? We're going to do some more of these on Wednesday. Okay, so don't panic and think, oh my gosh, that was it. Now we're on to 3-5. Nope. We'll camp out here for a little bit more on Wednesday. Yeah. Three halves, comma 7/8. It's just something in between.